Gravity. It's the force that keeps our feet firmly on the ground. It holds the moon in orbit around Earth. It keeps Earth circling our sun, and our sun on its grand voyage through the Milky Way galaxy. For centuries, we've pondered this fundamental force. Sir Isaac Newton gave us the first great mathematical description. He imagined it as a universal pull, an invisible string connecting every object with mass to every other object. An apple falls from a tree, the moon orbits the Earth. These were all part of the same grand cosmic dance, orchestrated by gravity's insistent tug, a force dependent on mass and distance. Newton's laws were incredibly successful. They allowed us to predict the motions of planets with remarkable accuracy. We could calculate the tides and understand the paths of comets. For over 200 years, Newton's gravity reigned supreme, providing a powerful framework for understanding the cosmos on a large scale. His equations worked beautifully for most everyday experiences and astronomical observations. However, as our tools and understanding grew, tiny discrepancies began to appear, hints that perhaps Newton's picture, while brilliant, wasn't complete story of this pervasive force, especially in extreme conditions not yet imagined in his time. Then came Albert Einstein, a young patent clerk with a revolutionary mind. In the early 20th century, Einstein presented a new vision of gravity with his general theory of relativity. He proposed that gravity isn't a force pulling things across space. Instead, gravity is the curvature of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The sheet warps and curves around the heavy ball. Now, if you roll a marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. This, Einstein said, is how gravity works. Massive objects warp space-time, and other objects follow these curves. Einstein's theory was a monumental leap. It explained anomalies in Mercury's orbit that Newton's theory couldn't. It predicted the bending of starlight by gravity, a phenomenon later confirmed during solar eclipses. General relativity has become the cornerstone of modern cosmology, describing black holes, the expansion of the universe, and gravitational waves. Yet, even Einstein's masterpiece has its limits. When we try to merge general relativity with quantum mechanics, the theory of the very small, things fall apart. We don't have a complete theory of quantum gravity, the realm where gravity meets the weirdness of the quantum world. This is one of the biggest unsolved puzzles in physics today. The quest for quantum gravity has led physicists down many fascinating paths. We've explored string theory, loop quantum gravity, and other exotic ideas. These theories attempt to describe gravity at the tiniest scales, where space-time might be made of discrete units or quanta. However, in 1995, a physicist named Ted Jacobson from the University of Maryland proposed something truly mind-bending. He suggested that perhaps we've been looking at gravity the wrong way around. What if gravity isn't a fundamental force at all? What if, instead, it's an emergent phenomenon, much like temperature or pressure, arise from the collective behavior of countless atoms? Jacobson's idea connects gravity to the laws of thermodynamics. Thermodynamics is the branch of physics that deals with heat, work, energy, and entropy. Entropy is a particularly interesting concept. Often described as a measure of disorder or randomness, it can also be thought of as a measure of information, specifically the hidden information in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. Think of an ice cube melting in a glass of water. The ordered structure of the ice gives way to the more disordered arrangement of water molecules. Entropy has increased. Jacobson brilliantly linked these thermodynamic concepts to the geometry of space-time. He started by considering a tiny local patch of space-time and the flow of energy across its boundary, known as a Rindler horizon. He applied fundamental thermodynamic relationships, particularly the connection between heat, entropy, and temperature, as established for black holes by Jacob Bekenstein and Stephen Hawking. They showed that black holes have entropy proportional to their event horizon's area and a temperature. Jacobson wondered if this was a clue to something deeper about space-time itself, not just black holes as special objects within it. Amazingly, by assuming that the relationship between entropy and horizon area holds true for these tiny local Rindler horizons, and by incorporating the first law of thermodynamics, which relates changes in energy, heat, and work, Jacobson was able to derive Einstein's field equations, the very equations that describe how space-time curves in general relativity. This was astonishing. It suggested that the equations we thought described a fundamental force could actually be an equation of state, similar to how the ideal gas law relates pressure, volume, and temperature for a gas, emerging from the statistical mechanics of its constituent particles. Gravity, in this view, is space-time's thermodynamic response to the presence of matter and energy. So, what does it mean for gravity to be an entropic force? An entropic force isn't a fundamental interaction like electromagnetism. Instead, it arises from a system's statistical tendency to increase its entropy, to move towards a state of greater disorder, or more precisely, a state with more possible microscopic arrangements. Imagine a long polymer chain like a strand of DNA in a solution. The chain can fold and coil in many different ways. Each configuration has a certain entropy. If you try to stretch the polymer, you are forcing it into a less probable, more ordered state, thereby reducing its entropy. The polymer resists this stretching, creating a force that tries to pull it back to a more coiled, higher entropy state. Let's consider another analogy, gas pressure. The pressure a gas exerts on the walls of its container isn't due to some fundamental pressure force between individual gas molecules and the wall. Instead, it's the result of countless tiny collisions of rapidly moving gas molecules. Each molecule carries momentum, and when it bounces off the wall, it transfers some of that momentum. The collective effect of these innumerable impacts, averaged over time, manifests as a steady outward push, the pressure. This pressure is a macroscopic phenomenon, emerging from the microscopic chaos of molecular motion, a system striving for maximum entropy within its constraints. Heat flow provides another useful comparison. Heat naturally flows from hotter objects to colder objects. This isn't because of a specific heat force. It's a consequence of the second law of thermodynamics. Energy, when allowed, will distribute itself in the most probable way, which usually means spreading out until temperatures equalize, maximizing the overall entropy of the combined system. The drive for heat to flow is an entropic drive. The system simply moves towards a state that has a higher number of accessible microstates, a more disordered configuration of thermal energy. This is a statistical inevitability, not a fundamental force pulling heat along. In Jacobson's picture, gravity behaves similarly. The presence of matter and energy in a region of spacetime can be thought of as reducing the number of available microscopic states for spacetime itself, or perhaps for some underlying unknown degrees of freedom that constitute spacetime. Spacetime then pushes back or curves in such a way as to maximize its entropy, given the constraints imposed by the matter energy. The curvature of spacetime, which we perceive as gravity, is essentially spacetime adjusting itself to reach a state of higher thermodynamic equilibrium, a statistical imperative rather than a fundamental interaction mediated by force-carrying particles like gravitons. Jacobson's theory, if correct, would revolutionize our understanding of gravity and the universe. One of its most profound implications is for the search for quantum gravity. Instead of trying to quantize general relativity directly, that is, trying to describe gravity in terms of discrete quantum particles, gravitons, Jacobson's approach suggests that gravity emerges from a more fundamental statistical theory of spacetime's microscopic constituents, whatever they may be. This is like understanding that fluid dynamics emerges from the statistical mechanics of atoms without needing to quantize the macroscopic equations of fluid flow themselves. It opens up entirely new avenues for research. Furthermore, this perspective drastically changes our view of spacetime. In traditional physics, spacetime is often seen as the fundamental stage upon which the drama of the universe unfolds. But if gravity is emergent, then spacetime itself might also be emergent, a collective phenomenon arising from more fundamental, pre-geometric degrees of freedom, much like the smooth surface of water emerges from the jiggling of countless H2O molecules. This means that the smooth, continuous space-time described by Einstein might just be an approximation valid only at large scales and low energies, breaking down at the Planck scale where its atomic nature will become apparent. This thermodynamic interpretation of gravity could also offer new insights into some of the deepest mysteries in cosmology, such as the nature of black hole entropy and the information paradox. If gravity is fundamentally linked to entropy, it provides a natural framework for understanding why black holes have entropy proportional to their horizon area. It might also shed light on the early universe, a period of extreme energy and density where quantum gravitational effects are thought to be dominant. Perhaps the very beginning of the universe can be understood as a thermodynamic process, a phase transition of spacetime's constituents. While Jacobson's theory is compelling and elegant, it's important to remember that it's still a theoretical framework. It doesn't yet provide a complete microscopic theory of spacetime's constituents. However, its power lies in its ability to reframe the problem of quantum gravity and to connect gravity with well-established principles of thermodynamics. It suggests that the universe might be even more interconnected and holographic than we previously imagined, with the laws of the large emerging from the statistics of the small. The ongoing exploration of these ideas continues to push the boundaries of our cosmic understanding, promising deeper insights into the fundamental fabric of reality itself.